Welcome to this revision video about critical path analysis. In this session we will explore how this time-based management technique helps break down complex projects into smaller activities, ensuring efficient use of time and resources. Consider a major project like building a new stadium. Critical path analysis helps project managers identify which tasks must be prioritized to avoid delays, and which can be performed simultaneously. This ensures the project is completed on time and within budget. In critical path analysis, a network diagram is used to map out the sequence of tasks. Nodes, represented by circles, indicate the earliest start time and latest finish time of an activity, while lines and arrows show the order of tasks. A description or identifier of an activity is shown above the line, whilst the duration of an activity is shown underneath. So, in our example, Activity A will take a duration of 7 days to complete. When more than one activity can start at the same time, we call them simultaneous activities. In this example, notice how tasks A and B can both start straight away. A dependent activity is when one task cannot start until another one has been completed. Here, we can see that activity D can only start once both activities B and C have been completed. Once we have drawn our diagram, the next stage is to calculate the EST and the LFT values for each of the nodes. We do this by undertaking what is known as a forwards and backwards pass through the network. Moving left to right, the earliest start time for node 1 must be 0, given that no activity has started at this point. For node number 2, we add the 0 for the EST of node 1 to the time it takes for activity A to be completed, which is 4. When more than one activity feeds into a node, on a forwards pass we always take the highest number value. So for activity D, the EST value is actually 11 and not 10. This makes sense when you think that for our example, we still have to wait for activity C to be completed before we can make a start on D. For a backwards pass, we need to calculate the latest finish time for each activity, moving from right to left, starting with the final node of the network. The LFT for this node must be the same value as its EST, as no other activity follows on from the last node. For node 5 we subtract the time taken for activity F to be completed from the LFT for node 6. So, the LFT value for node 5 is 15. That is, 20 minus 5 is equal to 15. The rest is all fairly straightforward, until we arrive at node 1. Here, we have two activities feeding into the same node, so we need to know which value to select. Did you remember? We always use the smallest value for a backwards pass. So, given that 11 minus 11 is equal to 0, is smaller than 5 minus 4, which is 1, we use the 0. Now that we have a completed network, we can identify the critical path. This is the minimum time required to complete the entire project. In diagrams, we identify the critical activities by drawing two parallel lines along the activity line. Tasks along the critical path have no float time. This means that their EST and their LFT values are the same. Any delay in these tasks will directly delay the project's completion, so identifying the critical path helps project managers focus on these tasks to ensure the project stays on schedule. This prevents bottlenecks and keeps the project moving forward smoothly. Additionally, knowing the critical path helps with resource allocation. Resources such as labor, machinery, and materials all cost money, so it is crucial that they are allocated efficiently. If we return to our earlier network diagram, we can see that the critical path falls along activities C, D, E, and F. That means that activities A and B are non-critical and have what is called float time. Float time represents the amount of delay that is possible on an activity, without affecting the project's overall duration. Calculating float time helps managers allocate resources more effectively, prioritizing critical tasks with zero float. The formula for calculating total float time is the LFT of an activity, minus its duration, minus its EST. So if we return to our diagram one final time, we can see that total float time for activity B is 1. It has an LFT value of 11, a duration time of 6, and an EST of 4. So, 11 minus 6, minus 4, equals 1. In summary, Critical path analysis is a powerful tool that helps managers with time management, resource allocation, and identifying critical tasks. If done correctly, it can provide firms with a source of competitive advantage by enabling them to get projects completed faster than rivals, and so offering them first-mover advantages. However, critical path is far from perfect. Often the type of projects that businesses undertake are unique and have not been done before. This presents its own challenges as there is a shortage of previous data upon which to base the critical path, meaning that errors and uncertainty are common. It also ignores external economic variables such as inflation and interest rates, which are hugely important in determining the costs of a project. Finally, it prioritizes time over everything else. This includes quality, which can mean false economy if a project is finished on time and within budget, but it proves to be of an inferior standard. I mean, would you really want to visit a stadium with a leaky roof?